Hi, Debbie. Can you all see and hear us okay with our current connection? Hello, Kingsport. Is there anybody there that can hear me and can reply back to make sure our connection is good? Hey, Debbie, can you hear and see us?
Hi, Rob. Yeah, we can.
Okay, good. You must have had an empty classroom because I got a little worried. I didn't hear anything from anybody when I asked you a minute ago.
Yeah, we've got a student here, but he's over in the corner. I didn't have the sound on. I've been down in the office.
Okay,
They'll be here in a few, maybe.
I'm just glad everything's going good so far.
Yeah, so far. Rob, can you fix that?
What are you trying to do, Deb? We have the content showing on our screen down here, if that's what you're trying to do. I'm not sure what you want me to fix, Debbie.
What are you seeing, Rob?
The computer.
Okay.
Are you having trouble getting it on your big screen in your room?
Well, I've got it on the big screen, but can you see me?
I can see you. It's a little bit backed out from you. It's not zoomed in.
Okay, I'll fix that.
So the first thing tonight, homework 5 for Tuesday. That's the 26th. So I went all the way back to chapter 8 because we hadn't had any out of there. So I'm just going to write them down without like talking too much. Don't freak out. Remember, the ones I underline are the multiple choice. We just got to come up with an answer. There's really nothing to do, whatever it takes. And then chapter 9. Those two are multiple choice there. And then chapter 12. One thing to mention here, that 1245, it's, if I remember right, it's a finite probability model. We give you a table and you start answering questions. Go back and look at the ones I did in class. The one about the coffee, the number of coffees drank per average one day, same style, just a different setup. And then chapter 13. Now, my thing I got to say about chapter 13 is, if I remember right, this problem here is going to require a Venn diagram. Remember we did one on Tuesday with the Venn diagram, where what it does, it helps me keep track of that overlap. Didn't we do the one about like degrees, associate's degrees, and men or something like that? Yeah. So look at that one if you want to see what to do here. And then 1349 is something else we're going to talk about today, which is called a tree diagram. Right, I'm just throwing that out there so you know how to attack it. I'm pretty sure the problems both say, one of them says use the Venn diagram, the other one says use the tree diagram. And then 1322 is the other thing. It's a multiple choice question, but it's dealing with what we're going to talk about here first, probabilities from a two-way table. Okay? So that's for Tuesday. And then where I left off on Tuesday was I'd written up this idea of conditional probability. And I'd said, well, look, we calculated conditional distributions before, right, in whatever chapter that was about two-way tables. And so with this conditional probability, what I'm thinking about is I'm thinking about being able to calculate probabilities from a two-way table. Now remember, a two-way table is the way we classified all our individuals when we had two categorical variables measured them, right? And we had like the row variable, the column variable, and all that stuff back in chapter 6. That's what we're talking about. Because what we did there before was we calculated all kinds of percentages, and anywhere I can calculate a percentage or proportion, now I can calculate a probability. Now, before I get too far into anything, a little bit of notation. This probability, so I got two events, B and A, like I always do. So the probability of B, given that A occurs. In other words, I'm reading that line as given that, right? Okay? So what I know is I have event B and event A, and this right here is I want the probability that event B will occur given that A has occurred. So we actually know something's happened, right? We know this event A has occurred. So this is the way to write conditional probability right here, right? That's a conditional probability, shorthand. Okay? The reason I'm giving you the notation is I'm going to write some of these problems out of this two-way table like that. But my other thought is this. one of the things I had told you on Tuesday was, actually, let's put two of them. You know, I talked about if I want the probability of A or B, right, and they're disjoint. Remember, disjoint means they have no outcomes in common. And then, remember, if I'm interested in the probability of A and B, I'm always interested in if my two events are independent or not, right? And if they're independent, we just multiply the probability. Well, here's the deal. If you've got two independent events, in terms of this conditional probability and this notation, two events are independent. That means the probability that B occurs is exactly the same as the probability that B occurs given that A has occurred. In other words, what I said in language on Tuesday was two events A and B are independent if knowing that A occurs does not change the probability that B occurs. You see my symbols here? That's exactly what that says. The probability of getting B is exactly the same as the probability of getting B that A has occurred. In other words, the fact that A occurs did not change the probability of B. That's that definition in words there, right? One other thing while we're here, multiplication rule. And then I'll get to the two-way table. On Tuesday, I gave you a multiplication rule for independent events. Now, I don't care if they're independent or not. If I want the probability of A and B, right, this is going to be the probability of A times that's irregardless of whether they're independent or not. If I want this probability of A and then B, that's the probability of A times the probability of B, given that A occurred. Right? So this is like your general multiplication rule. I wanted to throw it out there to you. I'm going to use it on you in a little bit, and I'm not even going to mention it. But this is what we're going to reason through it. But that's exactly what's going on. Probably more important than this is what does it mean for them to be independent? The regular probability is equal to the conditional probability, right? In terms of symbols, that's exactly what I wrote out in words on Tuesday. Now, when I say I want to look at probabilities from the two-way table, the kind of problem I'm looking at is problem, I think it's 1337. It's like a typical kind of problem here where I've got a two-way table, and I'm on page 326. Okay? And I want to look at problem 13.37. All right? It says college degrees. A striking trend in higher education is that more women than men reach each level of attainment. The National Center for Educational Statistics provides projections for the number of degrees earned, classified by level and by the sex of the degree recipient. Here's the projected number of earned degrees in thousands in the United States for the year 2019-2020. And what I see here is I have a two-way table, and I'm going to say a little bit about it. The row variable here is the person's sex, gender. The column variable is the degree. Right? So there's either female or male, and then my degree is either an associate's, bachelor's, master's, or doctorate. In other words, you know how I've labeled things for you? That's a 2x4 table. There's actually two rows, two categories of sex. There's actually two rows, and there's four columns. There's four different types of degrees. I don't pay any attention to the total, right? That just makes my life easier, but that's a 2x4 table. Now, the way we turn this two-way table into probability questions is I'm going to work like 3 or 4 or 5 different problems here, but the way all of them start is you choose a degree, recipient, at random. See that word right there? You're choosing a simple random sample of size 1 out of all the degree recipients for the 2019-2020 academic year. As soon as I see that word random, we're going to choose one at random, then I think, oh, now they're going to start asking me about probability. Is it the exact same kind of calculations we've done before? Yes, it is. And so I want to look at some of the problems I have here. Part A says, right, if you choose a degree recipient at random, what is the probability the person you choose is a man? So part A, I want the probability, and I'm not going to use capital A's or capital B's. I'm actually going to use the word that what we're looking for here. I want the probability that you choose a man. So the probability you choose a male. Let me ask you this question. You see this statement here? If I choose a degree recipient at random, what's my sample space look like? It's any one of the degree recipients in that year, and what I see is, you see the bottom right-hand corner of your table, it's 4,345. Now, somewhere there it tells me those numbers are in thousands. In other words, what they did was they chopped off 3 zeros. In other words, the number of individuals that's actually in this table is 4,345,000. So when I choose one at random, my sample space is all 4,345,000. Any one of the degree recipients will be a possibility, right? Okay? Now, what I want to know is if you choose one at random, what's the probability that you choose a male? Well, how many males are in this table? That is your second row total. You're going to get your 1758. And I want it out of the table total, which is your 4345. If you think about what that is, that's the proportion of males in the table, right? Well, if I'm choosing one at random, that's the exact same thing as the probability that you choose one at random. It's exactly the same as that proportion. If you pull your calculator out, you're going to get 0.405. In other words, if I was back in Chapter 6, I would tell you that there's 40.5% of the recipients in the table are male. But no, I'm in Chapter 13, and I chose one at random, and I want to know what's the probability you get a male. It's still 0.405. It's still 40.5%. Make sense? In other words, there's no difference here on how you calculate it. It's just we choose one at random. Now, hell, what's the probability you chose a male? All right? Now, are there other ones I can ask you like this? I don't want to jump right to conditional probability. I want to make sure you know that, I could have asked you about males. I could ask you about females. Could I ask you about the type of degree they earn? The level of degree. In other words, let's say I choose one at random and I want to know what's the probability that the person you chose has a bachelor's. Right? So now I'm looking at the columns instead of the rows. So then what do I ask myself? Oh, well, okay, so how many bachelors are in this table? There's 1935. How many individuals are in this table? 4345. Anybody got a calculator that will help me tonight, please? I didn't work that one out ahead of time. I mean, I'm going to give you, obviously, it's a little over 40%. We got 445. So I got 0.445. In other words, what this is telling me is 44.5% of the degrees earned here are bachelors. Well, if you choose one at random, what's the probability you chose somebody to have a bachelor's? It's 0.445. Is there anything special about me pulling out bachelors here? Could I pull out any of the other degrees and said, yeah, I need that total divided by the table total. Now, you see this number here. That's the table total, right? Okay? Because when I'm looking at the probability I chose a male or the probability I chose a bachelor's, I'm looking at everybody in that table. Everybody follow that, right? Because anytime you got a two-way table and you're asked for probability, you're going to have to form this fraction. Well, when you're just looking at, a column or a row, the number that's in the denominator is actually that row or that column total that you're asked about, all right? And then we come to part B with conditional conditional probabilities. We're going to know something about the person you chose. And this one says, what is the conditional probability that you chose a man, given that? So part B is, what's the probability you chose a male, given that? Now, you know, math people, you let me trade in 2 words for a line. Given that, you let me write a vertical line, I'm going to do that every time, right? So the probability you chose a man, a male, given that the person received a master's. That is a conditional probability. They don't have to tell me that. The dead giveaway is given that. Same given that I talked to you about in chapter 6. So there's a couple ways to think about conditional probability. We know the person we chose has a master's degree. So we're only looking at the ones that have a master's degree, and now based off of that group, what's the probability you chose a male? So what you're going to notice happen is, I'm going to start with the number that's in the denominator here. How many people in this table have a master's degree? And there is 938. Out of that 938, how many are males? I got 349. My friend's going to tell me what that calculates out to be in a second, but you see that part right there. You know the person you chose has a master's. That's where that 938 comes from. If I was back in chapter 6, I would tell you, we're only looking at that column and I'm ignoring the rest of the table. I know the person has a master's. Let's just look there. And now, what proportion or what percentage or what's the probability you chose somebody that has a male? What did you hear? Point something, something, something? 372? 372.
Say Omar.
All right, bud. Right? In other words, what I'm telling you is 37.2% of the people that have a master's degree are male. Right? That's what we're talking about. You choose one at random and people want to talk to you about probability. Is there anything special about male and master's degree? Let's do this. Let me do another one here. I know the book only asks you one of each type, but I want to throw a couple extras in here for you. And we're still going to choose one at random, but now what I want to know is, what's the probability that you chose somebody that has a doctorate, given that we know the person is female. So again, you've got to form that fraction. The number that goes in the denominator with your conditional probabilities is the given that part, what you know about the person or the individual, the recipient that you chose. And so we know the individual here is a female, right? So how many females are in the table? 25, 87. I would like to underline female and circle that to tell you that's where I came up with those numbers, right? I know. I'm not looking at everybody. I know the person I chose is a female. Now, out of that group, in other words, out of the first row, how many of those in the first row have a doctorate degree? And it is, in other words, what I'm doing is I'm fixing the row with the females, and that's all I see in the table. There's 2,587 of them, and 99 of them have a doctorate degree, and this gives me a probability of point something small. 228? So in other words, that's 22.8%, right? So the probability you chose somebody that has a doctorate degree, given the fact that we knew they were female, is 0.228. We okay with that? So here I fixed the row. Could I have asked you something other than doctorate? Yeah. I could have asked you about bachelor's, any of that. Yeah? You understand what I'm doing here? You see these guys here? Back in chapter 6, I'm just pulling out one piece of a marginal distribution. You see these here? I'm pulling out one piece of a conditional distribution. Right? So if you can do what we did in chapter 6, you can do it here, because your calculation does not change. It's just the setup. Oh, choose one at random. Now what's the probability? Now, there's a part C here. Right? We need to have a little talk about it, because I just said a little bit about independent. And it says, are the events, choose a man, and choose a master's degree recipient independent? So the question is, are they independent? And what I mean is male and masters. Now, if they're independent, knowing that the person got a master's degree should not change the probability of getting a male, right? In other words, if they're independent, this should be true. This, the probability of getting a male, should be equal to the probability of getting a male given that the person has a master's. Now, I got to go back to the other page. We did both of these pieces, right? Let me write that a little better. We did both of these pieces in part A and in part B. That's the ones I started with. The probability of getting a male given that the person had earned a master's. The reason I'm writing that question mark, because if these two are equal, then they are independent. In other words, one more time, knowing the person got a master's degree will not change the probability of getting a male. Knowing something up front did not help you. But if you look back here, the probability of getting a male was what? 0.405. So this is 0.405. The probability of getting a male given that the person had a master's degree was 0.372. They're not equal. So what does that mean? Not independent. And the odd thing is, knowing that the person you chose has a master's degree actually decreased the probability of getting a male. When you didn't know shit, the probability of getting a male was 0.405. As soon as you knew the person had a master's degree, it went down to 0.372, right? So actually knowing that the person had a master's degree decreased the probability of getting a male. Yes? The point is, they're not equal. That means they're not independent. Because my little definition says, if they're independent, those two things should be equal. In other words, knowing a master's degree had happened changed the probability of getting a male. Knowing that A occurred changed the probability of B occurring. B is getting a male, A is getting a master's degree. Are we okay with that, right? Now, you see number C, part C here? That's kind of shitty to ask. I can't ask you that on the test. I mean, how am I going to ask you that and be a multiple choice test? Now, do you see parts A and B? Oh, parts A and B, these are standard questions about probabilities off a two-way table. You know, just a straight up male, master's, or whatever the rows or columns are, and then this conditional probability. Now, I'm going to do this. I know the problem stops here, right? I got a part D. Okay? And I'm going to have a part D. Part D is, you choose one at random, and now I want to know the probability that the person you chose is male and got a master's. Now look, I know those two aren't independent, right? And I was supposed to be all crazy concerned about when somebody asked me about and independent. I just showed you in part C they're not independent. But the thing is, about this two-way table, I can calculate it directly without having to think too hard about anything. The point is, I know the number in the denominator is 4345. I'm looking out of everybody in the table, and the catch is they have both characteristics. They're male, and they have a master's degree. So you guys are already down looking at the table. So what are you looking at? You're looking at how many have a male and how many have a master's degree. I'm looking in the middle of the table, and what am I looking at? Male and master's degree is 349. Help. Tell me what you get.
0.08.
So in other words, there's 8% of these individuals at the table that are male and they have a master's degree. They have both characteristics. Now notice, that is not a conditional probability. You didn't hear me say anything about given that I knew something. I was checking for both characteristics, right? Okay, let's do another one of these. And also, I want to circle this. I'm looking at everybody in the table. So let's choose another one at random. This time I want to know the probability you chose a female. And the person has associates. Yeah, I'm jumping all over the table because I just need both characteristics, right? So this time I want the person to be female and have an associate's degree. It's an and problem. I'm not worried about being independent or not because I can just read it right from the table. What's the number in the denominator? You're looking at everybody in the table. No conditional probability. How many in here are female and have an associate's degree? I'm reading 756. If I'm wrong, you tell me. And I get a probability of point something, something, something. So 17.4% of the individuals in the table are female and they have an associate's degree. Or another way to say it is the associate's degree were earned by females. That means they're female and they have an associate's degree. Okay? Are we okay with these? So I could have asked you about female and doctorate, male and doctorate, male and master's, male, all kinds. Right? There's more than one question here. Now, is that D?
No, that was D. You said you had D.
I got an E coming, right? So I'm good on E now? Okay. Oh, no, I did 2 for each one of them. That's the reason I did, right? Now, this one here is a little bit different, too. Now, that was the and problem. And you notice I used everybody in the table. Now I want an or. I want the probability to get a male or the person has a master's. Now, you know, I'm like a little crazy dude when I see that or and that and all that shit. I'm supposed to be asking, are they disjoint or they're not disjoint, right? Because if they're disjoint, we just add them up, right? Now, if these are disjoint, that means there's nobody in the table that are male and have a master's degree. Obviously, that's not true, right? Because you know there's males in here that have a master's degree. So this is not disjoint. Right? So you just can't add them together. If you just add them together, you're going to count some of them twice. Now, do you remember? Yeah, I'm asking like you do. You haven't studied for anything yet. On Tuesday, I give you some kind of general addition rule that worked no matter whether they were disjoint or not, right? I'm going to write it out here in terms of what I'm looking at. If I want to find this, what I should do is I should find the probability of getting a male plus the probability of getting a master's. See, if they were disjoint, we'd be done, and I'd just write another equal sign and give you your answer here, correct? But they're not disjoint. So we have to subtract out the ones that are in common because you're going to count them in both of these. So you need to subtract out this. Male and master. Now, look, there's nothing crazy here because this is all out of the table total also. So what's the probability of getting a male? How many males are in the table? That was my 1758 over my 4345 plus, what's the probability of getting somebody that has a master's degree? Master's is 938 over 4345. And then what am I going to subtract out? The ones that are in common, the ones that are male and have a master's degree. Male and have a master's degree is 349. Does that make sense? Now, I'm going to rewrite this before I let her tell me what my answer is. What I'm looking at is this. The number in my denominator is the table total. I would add 758 and 938, and I would subtract out my 349. Right? I can put it all together as a single fraction, and I'm not trying to be like crazy math guy on you, all that shit. My point is this. You see that number right there? That's the males. You see that number right here? That's the master's degree. So what I did was I took the second row and the third column, right? When I'm looking at that table, I took the second row, added all them together to get my 1758. I took the third column, the one with the masters, and I got 938. Did we count anybody twice when we looked at that row and that column? We counted those right there twice, right? These. Those 349 showed up in the males, and those 349 showed up in the master's degree. You can't count them twice, so you subtract them out once. What do we get for an answer here? Would you turn out halfway nice? So the probability that you chose a male or somebody to have a master's degree is 0.54. If you like, 54%. I can't just do one of those and get away with this. I got to do one more, right? So let's say I want to choose a person at random, and I want the probability that you get a female or the person has a bachelor's. So you see that, or I'm supposed to ask myself, are they disjoint or not? In other words, are there any overlaps? Are there any degree recipients that are female and have a bachelor's degree? And the answer to that question is, obviously there is, so we're not disjoint. So I'm going to write it out long-winded here again. This should be the probability you get a female plus the probability you get a bachelor's. And you got to subtract out what you counted twice, the probability that the person is female and bachelor's. Okay? So then I just do each little piece. If you want, and we're far enough along here, I can do this to you. Right? I know I'm going to end up with that being my denominator. Then I'm going to have three pieces in the top, right? I'm going to have the number of females. There are 2587. I'm going to have the number that have a bachelor's degree. The second column is 1935. And then I got to subtract out the ones you counted twice because you looked at the first row and the second column. That number right there that are bachelor's and female, they got counted in that row and in that column. And there is, what is that, 1143? Then we pull the calculator out, add all that stuff up, subtract, divide by that, and I get a probability of 0.7. So the probability that when you choose a degree recipient at random, that you get a female or the person has a bachelor's degree, 0.778. That's every kind of problem I can think about from a two-way table. From very straightforward, looking at a row or a column, part A, to conditional probabilities where you know something about the person, to an and problem, where they're in common, to an or problem where you have to worry about this overlap, outcomes being in common. You got to worry about them not being disjoint. Now, can I say one other thing here, okay? I want to back up just a tad. And I want to back up to part B. You see where I've got those denominators circled? Right? Out of all the problems I've done from this two-way table, the only one where the denominator in your fraction is not the table total is the conditional probability. If we were sitting here in a probability class and we were going to spend a bunch of time on probability, what a conditional probability does is it cuts your sample space down. You don't look at everybody in the table, you know something about the person. So this first one here, I'm only looking at the master's degree, so I'm looking at that 938. The second one, I know something about the person. I know the person is a female, so I'm only looking at the 2587. Okay, you can cut the sample space down. You're not looking at everybody now. Something is telling you up front you know something, so you have to take that into consideration. That's my view here. Is there anything special about gender or sex and degree? Could I give you any two-way table and start asking questions like this? I've given you every question I can think of, every style off a two-way table where there's a probability. And what makes this any different than Chapter 6? my little green star there, choose a degree recipient at random, my ass is going to start talking about probability at that point. Are we okay? I guarantee you, when you get to your final, and even on my next test, you'll see a two-way table, we'll choose something at random, and we'll start asking these probability questions, and I will make sure you see all four of them. And what I mean is, part A, straightforward, part B, conditional. That one won't be there. An and problem, and an or problem. That's my four different types of problem from a two-way table. Okay? There's where we're at. Now, the other thing we want to talk about here is this. A Venn diagram was a tool. Right? It's a tool for keeping track of probabilities. Figuring probabilities off a two-way table, that's just, a way to calculate probabilities. My third thing out of this chapter is a tree diagram. Okay, so what I think about a tree diagram, it's a tool for keeping track of two things. Of the sample space S and probability. And then we'll go from there. So when I say it's a tool for keeping track of the sample space, in other words, what's your possible outcomes, and for probabilities of those outcomes in your sample space, my problem here is with why I need a tree diagram is, we're going to do more than one step. You're going to do this, and then we're going to do this, and hell, we might go 3 times. The one I'm going to talk about here, we're going to go twice. So there's like 2 steps to actually get to what your outcome is. And so I was thinking, I got like this typical kind of little problem here, and I would like to look at, what one did I have? I think I want to do 1312. It's a typical trying to tree diagram problem. Yeah, I got it drawn out so I don't screw you up in the middle here. And I'm on page 318. This is going to match you up to your homework problem. Didn't I have like 13.49 or something like that? It's going to match you up there because it needs a tree diagram. And this 1312, well, hell, it just caught my eye the other day for reason. It says white cats and deafness. Although cats generally possess an acute sense of hearing due to an anomaly in their genetic makeup, deafness among white cats with blue eyes is quite common. I didn't even know I could have a white cat that had blue eyes, so there we go. Okay? We can? I guess so. I didn't know that. Approximately 95% of the general cat population are non-white cats. Huh. In other words, not pure white. And congenital deafness is extremely rare in non-white cats. However, among white cats, approximately 75% have 2 blue eyes, right? Let me get all this straight. So, 75%, 2 blue. 40%, 1 blue. And only 19% with other colors. No blue. Are we okay? I'm just writing down what they got me here, okay? It says, additionally, among white cats, what is that? Oh, shit. 75% with 2 blue eyes are deaf. I should put deaf here. Sorry. And deaf. And deaf. And deaf. Right? Yeah. Only 19% with eye colors other than that are no blue, or deaf. Additionally, among white cats, approximately 23% We're only looking at eyes now. Forget the deaf. 2 blue. 4%. 1 blue. And then the remainder have eyes of other color. So if 27% have 1 eye or 2 eyes, how many have no blue eyes? Everybody understand how I just pulled that shit out of thin air? They only gave me the 23 and the 4. Where the 73 comes from, you understand. That had to add to 100%, right? That's how I knew that the other one had to be 73% no blue. Okay? And then it says do this. Draw a tree diagram for selecting a white cat. Outcomes are 1 blue eye, 2 blue eyes, or no blue eyes, and then deafness. In other words, like there's 2 steps here, right? Depending on what happens before. So the tree diagram might be a little odd. It's a tree laying on its side. You know, normally I think about a tree this way. My tree is going to go this way. So my first step is to choose a cat, a white cat, and one of 3 things are going to be true about that white cat. You're going to have 1 blue, 2 blue, or no blue. All right? So that's like my first thing to pay attention to. And then, depending on whether they have 1 blue eye, or 2 blue eyes, or no blue eyes, we know something about whether it's going to be deaf or not, right? So, 1 of 2 things can happen at this stage. Deaf. Can I do that? Not deaf, right? Deaf. Not deaf. Deaf. Not deaf. All right, so we're just doing that. So I'm keeping track of these 2 things. Now, in this tree diagram, I only have to go to 2 steps. Now, I need to put probabilities here. The probabilities goes on the branches, so that's the little lines I have here. So if you choose a white cat at random, what's the probability that you choose a white cat that has 1 blue eye? What percentage have a 1 blue eye? That's all the further I got to go, right? To me, this is just like calculating shit out of a 2-way table. If I know the percentage, then I know the probability. So the probability that you choose one with the 1 blue eye is, because there's 4%. With 2 blue eyes, .23% or 0.3, and then this was the rest of them, 0.73. So I'm labeling your branches with the probabilities, and I'm getting the probabilities from the percentages. All right? So I got the 0.04, 0.23, 0.73. Okay? What I just used to fill in that was this part right there. All right? You choose a white cat at random. There's 23% that have a blue eye. That means the probability of getting 2 blue eyes is 0.23. 4% have 1 blue eye. The probability of getting 1 with a blue eye is 0.04. Right? Same story. Now, I have to fill in the second set of branches. Now I'm sitting here looking, and I'm in the top here, right? So I've got a cat that has 1 blue eye. And now I want to know, if I've got a cat with 1 blue eye, what percentage of the ones with 1 blue eye are deaf? That's this part here. 1 blue eye that are deaf are 40%. So this is going to be 0.4. See, that's a conditional probability. That's the probability of being deaf given that the cat has 1 blue eye. That is 40% of those are like that. The probability is 0.4. What's the other branch got to be? They don't tell me anything about this one where I got 1 blue eye and not deaf. Those 2 had to add to 1. That's got to be 0.6. Right? So those branches there, because 1 blue eye, only 2 things can happen, deaf or not deaf. What about, you got a cat that's got 2 blue eyes. Now what's the probability that it's deaf? 2 blue eyes and deaf is 0.75. That's actually the conditional probability of getting a cat that's deaf, given that this white cat has 2 blue eyes. If that's 0.75, this has to be 0.25. The last one, no blue eyes, deaf. No blue eyes and deaf is 0.19. So in other words, the conditional probability that the cat is deaf, given it has no blue eyes, is 0.19. If that's 0.19, what's my last little branch there? I'm going to say it to you one more time. These branches here got to add to 1. These has got to add to 1. Those has got to add to 1. Those has got to add to 1. Because wherever we're at, that's all the possibilities you have. Now, the way you keep track of your sample space is you read the branches out. In other words, if I read all the top branches, what I have is here, my sample space. I'm going to write it like this. So if I read one blue eye and deaf, one blue and deaf. The next one is one blue and not deaf. Then I have two blue and deaf. Then I have two blue and not deaf, no blue, and deaf. And then finally, what is this? No blue and not deaf. There are, how many do I have here? I've got 2, 4, 6. That is your sample space. Those are your possible outcomes, right? One blue and deaf, one blue and not deaf. I'm just reading the branches out to get there. When I say reading out the branches, you notice the first one, I went here, then I went there, and that gave me that, right? So then I went to one blue, not deaf, two blue, deaf. That's your sample space. Now, how do I find the probability of each one of these? You multiply the probabilities that make up the branches that you walked out. In other words, for one blue and deaf, you're going to take 0.04 times 0.4. I'm going out those same branches. This is going to be 0.04 times 0.6. This here is going to be 0.23 times 0.75, 0.23 times 0.25. Out these, 0.73, 0.19, and 0.73 times 0.81. I'm multiplying the probabilities on my branches as I go out through them. Now, I didn't multiply all those out. I've made the tree diagram for us. We've kept track of my sample space. I know how to find each probability of each outcome in the sample space by multiplying out the branches. Then it comes here and it asks me, part B. What is the probability that a randomly chosen white cat is deaf? Shit. That's all they wanted to know? This is part A. So part B is, based off of your tree diagram, what's the probability that the cat you chose, white cat you chose, is deaf? Well, what ones is the cat deaf in? There's more than one, right? There are actually 3 of them. This should be the probability of one blue and deaf plus the probability of two blue and deaf plus the probability no blue and deaf. So we add those probabilities together. What is this one? This is my 0.04 times 4. This one here is my 0.23 times 0.75. And this one down here is my 0.73 times 0.19. I did cheat before we got here, and I've got these little probabilities. I got 0.016 plus 0.1725 plus 0.1387. I add those together. So the probability when I choose one of these white cats, that white cat is deaf, is 0.3272. Now, look, there's no way in hell that I could keep track of all this without this tree diagram because there's too many outcomes for me to think about on how to multiply and what I need to add up. Right? So notice what I'm looking at is I know the cat is deaf here. The cat is deaf here. And the cat is deaf there. Those are the three outcomes where the cat's deaf, irregardless of the number of blue eyes they have. I needed to add those three probabilities together, and that's what I'm trying to write here. And then I calculated each one of them, 0.016, 0.1752, excuse me, 0.1725, and 0.1387. We okay? Now, this is kind of long-winded because what? There was 3 branches at one stage and then 2 for the other ones. But that's what a tree diagram is good for, where you're checking for more than one thing. Okay? And while I have you here, you see how I'm multiplying out the branches, right? Just like I followed the branches to figure out what my outcomes were in the sample space, to multiply out those branches, I'm using the multiplication rule. I'm only going to write one of these at the bottom just so when you go back home and you're looking at this, I wanted to know the probability. For example, the very first one at the top. I want the probability of 1 blue and deaf. These are not independent. So what is this supposed to be equal to, my little formula? The probability of 1 blue times the probability of deaf given 1 blue. It just so happened, the way the problem is worded for me, that it gave me that conditional probability I needed. I knew this was 0.04 because 4% of all white cats have 1 blue eye, and they gave me this the probability of being deaf given 1 blue eye. That's all that stuff I wrote down first. That was the 0.4. So what we're really doing is going out to each one of the branches, we are doing the multiplication rule. Whether they're independent or not, and obviously here they're not, we're using that formula that I started here with today. The probability of A and B is the probability of A times the probability of B given that A occurred. Now, I think that should be the end of this chapter. Because see, the more simples I write, the worse shit gets. Right? We've got everything we need. You need to be able to do 3 things here. You need to be able to make a Venn diagram and read stuff off, and that's only where I've got 2 events. All those things I showed you about a 2-way table, you need to be able to calculate probabilities there. And then giving you something that looks like this, where there's like 2 things you're keeping track of, the number of blue eyes and deaf or not, you need to be able to draw yourself a tree diagram. And remember, how did he fill the tree diagram in? Because once you get it, it's not hard to deal with. How did he fill it in? How do you get the 0.04, 0.23, 0.73? Where do you get the point? Somewhere in the problem's got to tell me these things, right? The one I gave you for homework here, okay? I gave you, what was it? Anybody got it written up there? 1349? Yeah. So 1349 is about tennis serves. You need a tree diagram, right? The thing about that tree diagram is, once you win the point, you don't have to continue, right, once you get the serve in. So some of the branches might be longer than the others, right? There might be more than one step, and some of them might just have one. And the probabilities in 13.49 are written as conditional probabilities if you need to be able to go out the branches, right? So it's going to look similar to this. You need a tree diagram there, and it's about tense, okay? As far as I'm concerned, I'm done with this chapter because I got my 3 things in. And, I say that like that's no big deal. But I understand that I got all kinds of formulas running all over the place. Before I go to the next one, I got one thought for you. What are we concerned about when you see that? You agree? Or where I'm worried about disjoint. If they're not disjoint, I got to subtract the ones I counted twice, right? If they are disjoint, just add them together. What about this one? What are we concerned about when I see the probability of A and B? That's what I'm concerned about. If they're independent, just multiply the probabilities of each one. If they're not independent, there's going to have to be a conditional probability of B given that A occurred, right? To multiply the probability of A. It always makes a difference. And while I'm thinking about independence, see, I don't have any nice way of writing down disjoint other than just think about it. Do they have any outcomes in common? For independent, I do have a very nice idea, a really nice formula for this. They're independent if when you go back and look at your notes, that's exactly how I thought about males and masters, right? Turns out those two weren't equal, so they weren't independent. So here's the deal. We're done with probability. You'll hear the language again, but we're going to go back to our statistics stuff here to finish the rest of the semester. All right? And what we're going to talk about now is this is not going to go away the rest of the semester. You know, sometimes I tell you, you'll see it here, you'll see it there. This is not going away. And it's chapter 15. And it's something called sampling distributions. Now, I got a question for everybody. Do you know what a distribution is? Chapter 1. Distribution always tells me two things. It tells me what values my variable can take, and tells you how often it can take them, right? If I back you up to chapter 12, I'd talk to you about a probability distribution, and I'd tell you, it tells me the sample space and how to assign probabilities to outcomes, right? Still the same idea. So here's the thing. I want to bring up a little notation here. X bar, that's the X bar from chapter 2. That's the mean of a set of observations. Here, X bar is going to be what we call a sample mean. All right? In other words, we're going to take a sample and we're going to take an average over that sample. Whatever in the hell it is, I'm going to show you one in a moment. But it turns out, when you do that, when you take a random sample and you calculate the average across that sample, X bar is a random variable. For example, I'm going to take a random sample of 5 people from the class, and I'm going to calculate the average height. Can anybody tell me what the average height of those 5 people is going to be before I choose them and measure and take the average? And the answer is no. It's the same idea as this, flipping the coin, right? So in other words, this idea of choosing a sample of a particular size and calculating the average is unpredictable in the short term. Every time you do it, you can't tell me what it is, right? But if it's going to be a random variable, what do we know? It's supposed to settle down to a regular pattern of values, right? Well, the regular pattern of values is the sampling distribution. Anytime you take a sample and calculate X bar, hell, you can't tell me what the mean is going to be. But if I keep track of it over and over and over again, you're going to see a pattern. And the pattern is going to be described and going to be talked about in terms of a sampling distribution. That's the point here. That's where we're headed. Okay? Now, I want to look at this little question. The question I want to look at, and the typical kind of question we want here is how much on the average do American households earn? And I'm going to give you a per year. So this is a pretty typical statistics question, right? We want to look at American households and we want to know Okay, on the average, what's an American household earn per year? Now, are we going to talk to every American household in the United States? And the answer is, no, you're looking way too big here, right? So your population here, I'm going to take you back to that thought. All American households. Gigantic. We're not going to talk to all of them. So what are we going to do? Hopefully somebody's going to give me some kind of random sample here. And it turns out they did give me a random sample. It says the current population survey asked detailed questions about income. The 124,586 households in 2014 in spring 2015 had a mean income, total income of $75,738. So here's the thing. We took a sample, and I'm going to assume that if we're going to be talking about this, it's a random sample. I don't know if it's a simple random sample, stratified, systematic, multi-stage. I just know it's a random sample. And the sample size here is N was equal to 124,000 586 households that they actually sampled. Anytime we take a sample, we're always going to want to know what our sample size is. We're always going to use little n for that. So now we have a sample of 124,586 households out of all American households. So what they did was, they actually figured out, okay, so what was the average income for those 124,586? And it turns out that the average X bar, right, that's how you take the averages, our X bar, is 75,738. Now, I'm going to scream at you a second. You see that number they just calculated? This number right here, this is about, it's calculated from, it's about the sample. It's not telling me the population mean, it's telling me the sample mean, right? It's calculated from the sample. It's about the sample, okay? Now, what we want to do in the standard move here in statistics, we use it to estimate the mean income of all. I'm going to leave out the word American. We're looking at American households, of all households. Do you see this little guy right here? Do you remember when I drew the picture? Yeah, again. Back at the beginning of chapter 8, I drew you pictures, right? The population was up here. We had something we wanted to talk about. It was too big, so we chose a sample. And chapter 8 told us how to get a sample that was representative of the population, right? Then I'd come over here to the side, and I would draw you an arrow up, and I'd say I want to infer back. You see what I got starred here in green? This is the idea of inferring back. Let's use that X bar being 75,738, and let's try to estimate what the mean income of all households is based off our sample of 124,000 households. Okay? Now, what I just said, that is statistical inference. The way I think about it is the sample, we infer back to the population. It's this arrow going here that I was drawing in chapter 8. Now look, that's just a shorthand way for me to tell you I'm going to take what I've learned from the sample, and I want to infer back, and I want to draw conclusions about your population based off of what I've calculated and what I've learned from my sample. Now, here's the deal with all this. Random samples, which we've talked about. The other way for us to produce data was randomized comparative experiments, you realize both of these have the word random in it, right? They use chance, right? We use chance to choose a sample. We use chance to assign the subjects to the treatments in the randomized comparative experiment. The point is that they both use chance. So when you see we use chance, we, me and you, cannot guarantee that our results of inference are correct. That usually bothers a student at this point in the semester. Dude, we're going to do all this work, and at the end, you can't tell me whether we're right or wrong? No. Why do you think we stop talking about probability? See, because our inference methods, what's going to happen? There's going to come a probability attached to them. And look, what's the probability tell us? Doesn't the probability tell us how likely something is to occur? It doesn't matter whether I'm looking at a two-way tape or what the hell I'm looking at. Any kind of probability I calculate, it's always telling me how likely something is to happen or how likely something is to occur. So when I say our methods are going to come with a probability attached, it's going to be a success rate. In other words, if you use this method over and over again, this is how often you would be correct. This is how likely you are to be correct. You'll see us come with things like, the probability this method is correct is 95%. That means 95% of the time when you use it, you'll get a correct result. There's nothing wrong with that. The problem is the 5% that you know is going to be wrong. Okay? Now, before we go any further here, we need two definitions because in case you don't know, there's going to be two of everything running around. There's going to be your population. There's going to be your sample. There's going to be what we want to know about the population. There's going to be what we calculate from our sample. All right? So, I need this definition of parameter and something called a statistic. Where I'm at is, I'm on page 352 in your text. And, we actually, once we get these definitions, we're going to use this terminology. So when I think about a parameter is always about the population. And the catch is, it's usually unknown. I say usually. If it's not unknown, meaning you just go to the house. Sometimes they'll throw it in and say, okay, here's what it is. But, look, I always think about a parameter as being some unknown quantity about a population. If we knew it, we wouldn't be taking samples. We wouldn't be doing any of that. Okay? So we always speak of a population parameter. Okay? And then there's a statistic. This is about the sample. And what I mean is, it is calculated. From the sample. So we think of sample statistic and population parameter. Now, we're going to have a favorite parameter for a while, and we're going to have a favorite statistic. Okay? So my notation is this. And then I'm going to go back and look at that average household income. We are going to use mu for the mean of a population. In other words, this will be your parameter. Mu will be a parameter. It will be some unknown mean about some given population. We will use x bar as the mean of a sample. This is going to be your statistic. Now, the way this game is played, and I apologize for calling it a game, the way this is worked out is we always want to use whatever our statistic is to estimate whatever that unknown quantity, that parameter is about our population. So that's in general. This idea here about mu being the mean of the population being my parameter, x bar being the mean of the sample being my statistic, that's going to stay with us for quite a few chapters, and eventually we don't always want to know about the mean of a population. We might want to know something else, so my parameter will change. Obviously, my statistic will also have to change. We'll have a talk about that when we get there. Now, in general, we use the statistic, and I'm going to put it like this just one time, the sample statistic to estimate the population parameter. That is in general. You will see me do this all the way through the rest of the chapters. I always want to use my statistic, what I've calculated for my sample, to estimate my parameter, what I want to know about my population, right? I figured if I wrote these words together here, that would stop you from doing some crazy stuff. You know, he's talking about a sample statistic, a population parameter. We never talk about a population statistic or a sample parameter. I don't know what the hell you're talking about. It's either a sample statistic or it's a population parameter. About the population or about your sample. That's the general thought. Well, I already know what my parameter, what my statistic is going to be, so I'll say this like maybe 150,000 times between now and next Thursday. We want to use x bar to estimate mu. I want to use that sample mean, that sample statistic from my sample to estimate that population parameter, that population mean that I want to know about. Okay? So, back to the one about household incomes. X bar, what was that number? 75,738 or something like that? That is your statistic. That is your sample statistic. The mean here, I don't know what the hell it is. I don't have that number. So what it is this is the mean household. Let's go like this. It's the mean income of all households. And this is, in this case, that is your parameter. I try to be consistent with my colors. I know you don't get the right colors, and I'm so crazy about reds and blues. That should be my statistic. Of course, come Tuesday, I may flip them back and forth, but at least for the day, I try to stay consistent. Right, so what did we calculate from our sample, 144,000, whatever it was, that 75,738? That was your statistic, right? That was your sample mean. It came from the sample. Well, what was we trying to estimate? What was my question actually about? It was about the mean income of all American households, right? That was a mu, and that was your parameter. Yes? We always use mu for the mean of a population as your parameter. We always use x bar because we're going to calculate x bar from the mean of a sample. Okay? Now, my first thought is this. Is this shit even a good idea? And what I mean is, not this part. We calculate here, right? I mean this over here. You see that right there? We use the sample statistic to estimate the population parameter. Is that a good idea? Well, forget that. I want to use x bar, that's my statistic, to estimate mu, which is my parameter. Is this a good idea? Well, our first thought about that being a good idea is something called Statistical Estimation. Look, that's just a fancy statistician's term for taking what you've calculated from your sample to estimate what you want to know about in the population. And the other thing is this law of large numbers. See, this is our first reason why all this is a halfway decent idea. I'm going to say a good idea. Okay? I've already told you that if I have random samples, X bar is going to be a random variable, right? I started that chapter with that. We want to describe the behavior of X bar, your sample mean, your statistic, okay, by a probability model. Well, if it's a random variable, then I should be able to come up with a probability model to describe its behavior. Now, you see this word here? I don't get to use this word very often in a math class, as a behavior or something. What I mean is this. Let's do this. So the first time they took 124,000 households, they got an average household income of being 75,000 or something. Suppose we do it again. Are we going to get the exact same average again? Are we going to get 75,000, whatever that is? What about if I do it a third time? Am I going to get a different one? A fourth time? Every time I do it, I'm going to get a different average over a different 124,000 whatever households, right? In other words, that's what I mean by behavior. As I go from one sample to the next, X bar is going to change its value. That's called sampling variability. One more time. I go from this sample to this sample. The samples were all the same size. Obviously, they got different households in them, so I'm going to give you, obviously, you're going to get a different X bar. Every time I do this, I'll get a different X bar. I mean, like, what the hell is the chances that I choose 124,000 and the different ones and I get the same X bar? Ain't no way in hell. Right? Every time I do this, I will get a different X bar, and so I want to describe that behavior. What does it look like when we go from one sample to the next? What I mean is, what's the possible values I can get for X bar? What's the different sample mean? What's the different values in my statistic? That's what we're looking at. Okay? Now, the thought is this. And I kind of want to get to the point here. You can read this example 15.2. I mean, the reason I'm not going to talk about it, if you'll come over here and look at page 355 in your text, there's a figure. There's a figure 15.1. And I could swear I've seen that one before. Do you remember when we tossed a coin back at the beginning of whatever chapter that was? You flipped the coin and calculated the proportion of heads, and it bounced around and finally settled down to like 50%? The guy picked the graph up and he put it in this chapter. Right? And what he's doing is, he's doing this. I'm going to make it very simple. I don't really care about dimethyl sulfide odors and wine. What he does is, he chooses a person at random. Or in other words, let's do it like this. He chooses a household at random. And he looks at the income, right? And so he plots that income when n is equal to 1. And then he chooses another household and he takes the average of those two. And he plots that average. And then he takes a third one and he takes the average of those three. He takes the fourth one. He takes the average of those four and he plots those. And what happens is, eventually, as he keeps increasing his sample size one at a time, his X bar gets closer and closer to the mean of the population. Well, what guarantees this is, page 354, something called the law of large numbers. It seems reasonable enough that it would work like this, as long as I'm choosing in a random fashion. And what it says is this. Draw observations at random from any population with finite mean mu. In other words, you got a population mean, mu. Right? That is your statistic. Okay? As the number of observations drawn increases, in other words, as the sample size n increases, that's the same thing as the number of observations increasing, right? So as the sample size n increases, as you keep adding more and more individuals from the population in your sample, the sample mean, x bar, gets closer and closer to me. Well, look, I know it's time to go to the house, but here's the thought. Think about it. Didn't I always give you this little thought about larger samples give you more accurate results? That's what the hell this is telling you. As your sample size increases, x bar becomes a better and better estimate of mu, right? It gets closer and closer to mu. What's the best thing that ever happened? Well, when we take our sample, we do a census, right? We get everybody in the population, and my x bar is exactly equal to mu. You can also think about it like this way. As your sample size increases randomly, your sample becomes more representative of the population, right? So the more representative it is, the larger your sample size, the closer x bar gets to mu. Okay, so when we come back on Tuesday, that's the first reason why this is a good idea. Because if I have the time and money to take larger and larger samples, I am guaranteed that x bar will get closer and closer to that population mean mu. In other words, my statistic will get closer and closer to my parameter. Be careful going to the house. Don't forget my homework problem. We will see you on Tuesday.